again, the question is, you are playing Snakes and Ladders with this specific board, and it's kind of a baby board, so we can calculate easily what's going on. And there is exactly one ladder from 4 to 7. There's exactly one snake down from 8 to 2. And the question is, what is the probability that in 3 rolls you are exactly on square 7? So kind of a basic probability calculation. And let me see what you guys said. What did people say? Okay. 3 people said 15, most common answer, 19, 25. One person said 2, 10, 14. One person said 23, 26, 30, 34. People are all over the place. I will say, one person got it right. It's 23. So if you said 23, congratulations. Maybe you were just getting lucky. Why did I have you guys work on this? The reason I had you work on this is because if you sort of do this the sort of pedestrian way, like you were taught in intro stats or intro probability, which is to count the number of ways you can get there, it's a real pain. It's like a really horrible problem to count the number of ways. And I think this is what most people did, is they tried to say, how could we get there? Let's start thinking of ways. Well, like one way is we could get to square 4, and then the ladder takes us up to 7. So we could get to square 4. So we could roll like a 1, and then a 1, and then a 2. Or we could roll like a 2, and then a 1, and then a 1. And you can start writing all these down. So this is like one method of solution, is to just start writing down everything. Let me start doing this. Okay. So snakes and ladders. Snakes and ladders. And this is the sort of like ordinary way of doing probability, is to just count up the number of ways, right? So count ways. And so maybe you could say like, you get to 4. That's like one case, get to 4. So you go like 1, 1, 2, 1, 2, 1, or 2, 1, 1. Those are the 3 ways 3 dice can add up to 4. So that's three ways. And then, so you get to 4, and then the ladder takes you up to 7. So that's something that could happen. Or you could get to 7. You could get to 7. And so maybe there's a bunch of ways you can get to 7. Maybe there's like 1, 1, 5, 1, 2, 4, 1, 3, 3, 1, 4, 2, 1, 5, 1. Okay, those are all the ways you can do it with the first dice being 1. Then there's 2, 1. Okay, that is up to 3, 4, 2, 2, 3, 2, 3, 2, 2, 4, 1, 2, 5. Okay, 2, 5 doesn't work because you're already at 7. Okay, so there you go. Those are the ways with 2s. And you can keep going like this. 3, okay, I'll write ... and you get the idea. Okay, so you just write up all the ways that you can do it. And you sort of like think of all these ways. I have already made a mistake here. I have already made a mistake. And so the point I'm trying to make is that this is a bad way to do it, because first of all, it's exhausting. Second of all, very easy to make mistakes. Does anybody see the mistake that I made? Yeah.
Could it be that like you can get to 4 on one roll, and then you're automatically at 7, so that would, like, after 3 rolls, you'd already be at 9 already?
Yeah, I think you're, okay, yeah, this is great. So I guess you're pointing out that I have more cases I haven't done yet, right?
Well, I was just thinking, like, yeah, okay, sure.
Yeah, I guess what I'm trying to say is, not only are there more cases I haven't done yet in the ... but some of the cases that I say end you at square 7 after 3 rolls don't actually end you at 7 after 3 rolls. So I made an actual mistake and counted something that I shouldn't be counting. Yeah.
So 1, 1, 3, and 2, 2, 3 get you 4.
Yes, this is exactly it. Okay. So if you roll 1, 3, 3, you're like, those add up to 7. So you're on square 7. That is false, because 1, 3 adds up to 4. So in your first 2 rolls, you end on the ladder that takes you up to 7. So after 2 rolls, you are at 4. You are at 4, and then you take the ladder up to 7. So if you roll 1, 3, 3, actually you will be on like square 10, or you'll just be at 9 and be done. Because after 1, 3, you end at the ladder. The ladder takes you up to 7, and then you roll again. So you're not at 7. So this one is actually wrong. So if you want to do it this way, you have to say get to 7, and you have to say without hitting 4 first. Hitting 4 first. And then you have to cross out some of these. So this one is wrong. Which other one? This one is wrong. This one is wrong. So not only are you going to be kind of writing all these crazy combinations out, but you have to be really careful about all these like weird edge cases. And it's super annoying. All right, yeah, I guess there's other ways, and I guess let's in the benefit of me not spending too much time writing down all these ways, let me just show you the website, which has all the ways. Here it is. Okay. Snakes and ladders. Here's the board written out with emojis. So here's the snake that takes you from 8 to 2, the ladder that takes you from 4 to 7. And if you want to do it this sort of exhaustive way, then here are the ways you can do it. So I wrote them out as R stands for roll, and then I wrote down the things that happen to you. So here is R, 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 and then a ladder from 4 to 7. There's 3 ways, 1, 1, 2, 1, 2, 1, and 2, 1, 1. This is R, R, R directly to 7 without hitting a snake and a ladder. And here is my solutions that sort of cross out ways that hit something along the way, right? So you write down all the ways to get to 7, and you cross out the ones that would have hit the ladder. And then there's a whole bunch of other ones. So here is R, R, get to the snake, and then roll again. And there's some number of ways, and so on and so on. And you can write these all out, and you super make sure you didn't miss any, which last year when I did the problem I did, and then some students corrected me. And the answer is there are 23 total ways. Okay, so this is a valid solution, but as I have written over here, this is horrible. Okay, horrible. So we're going to learn a better way, and the reason I made you guys try to do that is to try to help you appreciate that this is a bad way to do the problem, and we should hope that there's a better way. Before I tell you the better way, any questions or comments about the sort of bad way? All right. Did anybody try a sort of different approach other than this exhaustive, like write them all out? Yeah.
So as you mentioned Markov chain before, so I tried coming up with a ray transition diagram or the probability matrix and then cubing that so if I could find it, but then.
Yes. Okay. So that is essentially, if you know what a Markov chain is, the timer reset on me. Okay. If you know what a Markov chain is, that is the magic solution. That is what we're learning, how to do it with a Markov chain. And a Markov chain uses one very important property of this problem. So the system we're doing could, in principle, handle any sort of weird game. But this game is not just any sort of weird game. It has a very nice property, which was mentioned in the video. And we're going to exploit that property to help us solve it. And that property is the fact that where you are, once you're somewhere, it doesn't matter how you got there. So this is the Markov solution. By the way, Markov was some Russian mathematician, and everything is named after him. I guess he discovered this stuff. So we're going to use what is the so-called Markov property, and that is going to be like a little hack that's going to let us drastically simplify what's going on. And the Markov property says very roughly that once you are somewhere, once you are, let's say, at a square, at a certain square, it doesn't matter how you got there. Okay, and this property that once you're at a certain square, it doesn't matter how you got there, it's going to let us sort of group together a lot of calculations and calculate sort of step by step. You can kind of see that in the very exhaustive solution I was writing before. Like, for example, this one, 1, 2, 1, and 2, 1, 4, they both start with something that ends on square 3. So I could have sort of grouped together this outcome and this outcome by saying, what are the chances to get to square 3 in 2 rolls? And then what are the chances to end on square 7 once you're on square 3? And this is exactly the kind of division that we're going to do. So this is just to give you the idea. Another sort of way to take this Markov property is I'm going to take the original problem and I'm going to turn it into a harder problem, which sounds crazy, but let me write it down. So the original problem is find the probability that you are at 7, let's call it S7 after 3 rolls. Actually, let's not call it S7. Let's call it square 7. At square 7 after 3 rolls. That was the original problem. I'm going to make a new problem, and the new problem looks way harder, which is you're going to think I'm totally nuts for making the new problem, but you'll see why. And the new problem is find the probability you are at square x after t rolls for every x and t. Okay, so of course, the new problem contains the original problem by setting x equals 7 and t equals 3. But the new problem is like a whole bunch of extra stuff. And any reasonable person, if you had a final exam in front of you and the instructor was like, pick one problem and do it, nobody would ever pick this new problem, right? You'd be like, of course I'm going to pick this one, it's easier. But what I'm going to tell you is that the new problem is actually easier. In the same way, it's easier to climb a ladder that has 3 steps than it is to climb a ladder with just something on the third. So you should think of the original problem I gave you. It was like there's a ladder, and I broke the first 2 rungs, whereas in this new problem, I've put them back. So, and this is really like t equals 1, t equals 2, and t equals 3. And here I just said, please find it when t equals 3. So, like the original problem I gave you was like, please climb a ladder where you're only told to go to the 3rd rung. And in the new problem, I'm telling you, climb all the steps of the ladder. That will give you the answer. And what's really going to happen is knowing what happens when t equals 1 will help us figure out what happens when t equals 2. And knowing what happens when t equals 2 will help us figure out what happens when t equals 3. So we're going to kind of like build up. And the Markov property, this property that once you're on a certain square, it doesn't matter how you got there, that's going to be, say that if you know everything about t equals 1, then you'll be able to solve t equals 2 completely. And if you know everything about t equals 2, then you can solve t equals 3 completely. The only thing that matters is where you are sort of at time 2, not the path that you took to get there. Okay, so that's like a very general overview. And then we're going to get into the nitty gritty in a second. But any questions or comments so far? But this is like, I will tell you, this is like the thing that's going to be in every single class in the course is these Markov things. They're going to get more complicated. We're going to add on actions and rewards. But this thing is going to be in every single class. So it's good to get it right. Questions or comments so far? All right, let's see how to do it. And to do it, I'm going to use everybody's favorite programming language, which is a spreadsheet. So we're going to do it in a spreadsheet, and we're going to answer this question, find square x after t rolls. Okay, here's my spreadsheet. Okay, let me see if I can find a way to make this look good. Okay. Okay, so here is my spreadsheet, and I have tried to zoom in the right amount. Can I make these any different? Okay, hopefully that's visible. Oh, the current window is too small. Thanks. Okay. So here's what I have in my spreadsheet, and we're going to fill it in sort of one row at a time. And the rows are labeled round 0, round 1, round 2, round 3. And our question is find the probability to be at a certain square at round 3. So we're going to fill in as we go. And the columns are square 0, square 1, square 2, all the way up to square 9. And we're just going to write down the number of ways to get to each of the squares in each of the rounds. And this is exactly solving what I called the new problem. And you're going to see how solving it at round 0 is going to help us solve it at round 1. Solving it at round 1 is going to help us solve it at round 2, and so on and so on. Okay, let's start with round 0. Round 0 is like before you've done everything. And in round 0, there's a 100% chance you're in square 0. So this is like before you've rolled the dice, you start in square 0, you're always in square 0 100% of the time. Then round 1, you roll the dice, and then you move your piece, right? So you roll the dice and you move your piece. And I have divided round 1 into 2 parts. There's the pre-SL and the post-SL. SL stands for snakes and ladders. So I'm going to first move you, and then you're going to be somewhere, and then I'm going to apply the snakes and ladders, and you're going to see where you are. And here's the nice thing. If you start in square 0 and you roll the dice, then you're going to be in either 1, 2, 3, 4, 5, or 6. And each of them happens with a 1/6 chance. So I could put 1/6, 1/6, no, not 2/6, 1/6, 1/6, 1/6, 1/6, 1/6. And then I could put 0, 0, 0. There's going to be a lot of zeros, so I'm just not going to write things when they're 0. I'm just going to leave them off. That is the probability to be at squares 1 to 6 and the probability to be at 7, 8, and 9 after one round before the snakes and ladders are applied. And then we can apply the snakes and ladders. If you're at square 4, you get moved to square 7 automatically. So after the snakes and ladders, what does it look like? I guess it's a copy of this. And then I'm going to delete, or let me cut and paste the 4 into the 7. Okay, change the color. Let me just delete it. Delete and a 1 to 6. So those are the probabilities to be anywhere after one round after the snakes and ladders. And that's actually what we're interested in. This is just like a helper to make sure we have we did it all right. Okay, questions or comments about that? All right. Yeah.
I love spreadsheets.
You love spreadsheets. Great. Yes, this is good. This is very good. I'm very sorry to tell you this is going to be the only class where we do spreadsheets. So after today, we'll learn how to do the spreadsheet in Python, and then we'll do it all in Python. Python's like spreadsheets, but even better. Okay. Okay, this is all totally correct. I could keep going. There is one small thing I'm going to do just for visibility, which is it's kind of annoying to write the 6 to 6 to 6 to 6. I'm going to just write 1, 1, 1, 1, 1, and then I'm going to keep track of a multiplier in this little column over here that's going to say 1/6. So I'm just going to write 1, 1, 1, 1, 1, 1. We really do care about probabilities. We want to know the probability. But because the probability is always something divided by 6, let's just keep track of the number of ways and then remember that we're supposed to divide by 6. So I want you to think of what's on the board now as exactly the same as what's on the board before. It's just like easier for your eyes to look at. Okay, great. That was round 1. Now let's figure out round 2. And this is like, I think this is like the big innovation. This is like the big way of thinking about it. When you figure out round 2, all you got to do is like repeat what we did from round 0 to round 1, but do it for each of these positions, right? So we said at round 0 you start here, and then you like moved over to these places, and then the snakes and ladders happened, and then moved you again. But like each of these things is going to sort of like blow up into like new outcomes, right? Like if you're in 1, you will move either to 2, 3, 4, 5, 6, 7, or 8. No, you won't move to 8. 1, 2, 3, 4, 5, 6, or 7. If you're in 7, you'll move to 8 or 9. And so sort of like each of these outcomes will sort of spread itself out into the other states, and then we just add up what happens. And to do that, I have added some extra rows, which is I said round 2, instead of doing it right away, I said from S1, from S2, from S3, from S4. So I'm sort of doing it starting point by starting point. So for example, S1, oh, I lost the labels. Let me see if I can get the labels back with some magic. There's a command called freeze. I gotta freeze the row. More row actions. Freeze. All right. Well, okay, great. So here we go. Okay. Let's do it like that. Okay. So, all right, there we go. So here is after round 1. And then I'm going to say only considering what happened from S1. So there's one way to get to S1. Where would you go? And this is, again, you're rolling a dice. So what are the outcomes? Well, you can go there, or there, or there, or there, or there, or there. Yeah, that's it. There's 6 of them. So this is saying if you're at row 1, then you move to any of those places. There's one way to do it, right? There was one way to get to state 1, and then you have to roll exactly one outcome on the dice to get to any of these squares. And from S2, it's the same thing, but shifted over by 1, right? So from S2, you're here, or here, or here, or here, or here, or here. From S3, you're here, or here, or here, or here, or here, or here, right? So from S3, you can either go to S4, 5, 6, 7, 8, or 9. From S4 is the first interesting one. Who can tell me what do you do for S4? Yeah.
Does square 9 get increased to 2? Something like
It
that.
that would happen if there wasn't. You're totally right. You're thinking of the right thing. I'll call on you again for S5 and you'll get it exactly right. But S4 has another weird, annoying thing. Yeah.
It'll just be blank because you can't start from S1.
It's just blank. So there's no way to get to S4 after round 1, right? This is blank, which means 0. And so this one should be blank too. Technically, it should be all zeros, but it is annoying to read with all zeros. So S4, completely blank. There is nothing coming out of S4 because there was no way to get into S4, right? There's no outcomes that lead you to S4 after 1 roll, and so there's no contribution after 2 rolls to where you would be. S5 is also interesting. So S5 is 1, 1, 1, 1. What number do I put here? Now I'll call on you. 2, yes. So there's 2 ways to get from S5 to square 9. You can roll 4.
Would it be 1113?
It should be 1113. Yes, very good. Okay, yes, I was going to say. All right, very good. It should be 1113. There's 3 ways to get from S5 to S9. You can roll a 4 or a 5 or a 6, and all 3 of those rolls will lead you to S9. So there's 3 ways to get from S5 to square S9. Yeah, that's right. So the trick is the number in each row here should add up to 6 because there's 6 total rolls of the dice, and we're representing all 6 of those ways to do it. Okay, That's S5. S6 is 1, 1, 4. There's 4 ways to go from S6 to S9. And then there is, from S7, you can be at S8, or 5 ways to get to S9. Wait, is that true? Okay, I don't want to do this one. This is another one. No, wait, okay, it's all fine. Okay, this is 1, 5. Okay, and then S8 and S9, these are also blank because there was no way to be in S8 and S9 after round 1. Maybe I really do need to take Google's suggestion and zoom out a little bit at this point. Okay, so you can see everything. All right, so these are the number of ways to get to all of these locations, specifically from these specific paths that you went to at round 1. Once again, all of these things you should think of as probabilities by just multiplying them by the right multiplier, which is 1 over 36. 1 over 36, 1 over 36. Maybe I can, I remember if you pull down 1 over 36, it tries to change it. So let me just write it out. Okay, 1 over 36, 1 over 36. All of these will be 1 over 36. Okay, are there any questions or comments so far? So this is how to end up somewhere after 2 rolls based on where you were after 1 roll. It's good? Okay, so now the question is, what is the total probability after 2 rolls to be somewhere? So this is what I really want to do, is I want to make the equivalent of these 2 lines. Round 2, where are you? Before the snakes and ladders and after the snakes and ladders, and that's going to go here. And now I want to just like no longer care about which one you went through on round 1. And to do this, you have to do a very simple operation to all these numbers up here. You have to add them together, right? So how can you get to S4? Well, you could have got to S4 through S1 or through S2 or through S3. There was one way, or one way. How many total ways are there to get to S4? 1 plus 1 plus 1 is 3. So the next line I'm going to do is just to add these up. So this one will be 3, like I said. I believe this is 2 and 1. Let's see if I'm right. 1, 2, 3. This one is 3 again because this thing was missing. So it's 1, 2, 3 from this sum. 1 plus 1 plus 1 plus 1 is 4. Okay. And then 1 plus 1 plus 1 plus 1 plus 1 is 5. And then over here, we got 1 plus 1 plus 1 plus 1 plus 1 is 5 again. And over here is a big number. There are a lot of ways to be at square 9. 1 plus 3 plus 4 plus 5 is 13. Okay. And if we did it correctly, this should add up to 36. Because these things are all paths. They're supposed to represent probabilities. And you should be somewhere. You should be on some of these squares. So it should add up to 36. Someone check if it adds up to 36. Maybe I made a mistake.
You're good.
It's good. Okay, fantastic. Let's also do a sneaky check. I have a little. I did it at home. Okay. 1, 2, 3, 3, 4, 5, 5, 13. 1, 2, 3, 3, 4, 5, 5, 13. Okay, great. We did it. All right. So this is before the snakes and ladders are applied, and we did it by doing this sort of addition thing. All right. Now we're going to apply the snakes and ladders, and once again, the snakes and the ladders are exactly the same thing, right? So I'm going to copy and paste it. Except for you apply the snake and the ladder. So what do the snakes and ladders do? Well, if you were on 4, I'm going to change that to a 0, and I'm going to add the possibilities to 7, right? So 7 got 3 extra possibilities because you could have been on square 4 and then taken the ladder up to 7. And then square 8, that gets deleted, and then the 5 possibilities get added on to 2 for 6. Okay. So it's 6, 2, 0, 3, 4, 8, 0, 13, unless I made a mistake. 1 out of 36. Let's check the cheat sheet. 6, 2, space, 3, 4, 8, space, 13. Okay, great. Fantastic, we got it. So that is how to do it. And you might think, okay, this is like about as much work as adding them all up, right? Like, is this really saving us a lot of time? So far, it seems like this is a huge hassle. And I think really the time saving starts now. And because we've sort of grouped together, like for example, this one has 8 possibilities that are all grouped together. These are 8 different ways that 2 rolls can lead you to square 7. And now we don't need to worry about which of those 8 rolls it was. Like all of these details of, were you on square 1 or square 2 in round 1, all of that is condensed into one number. And so when we go to do round 3, we're not going to have to do it again. So it's sort of like the same amount of work every time. It doesn't get more and more complicated as you add more layers. And another way to say that for people who like sort of complexity theory is that the number of ways you would have to sort of write down over here scales like to the power of t. So the work to do this. So the original method, the amount of work you have to do is like 6 to the power of t, where t is the time that I asked you. But over here, in this new method, the new method, it's linear in t. Work is, let's say, c times t. So every time you want to do this, crank this spreadsheet by 1, you have to do all this work that I just did. But it's not like it gets harder. It's sort of the same amount of work every time. If I said do it 100 times to find what happens after 100 rolls, you would just repeat this operation 100 times. It doesn't get more complicated as you go. Okay, great chance to ask questions or comments here before I go to round 3. I think you've already seen the main idea. We're going to repeat it one more time. But this is a fantastic place for a question. All right, let's do round 3. By the way, if you just wanted the answer to the original question, which was in round 3, how do you get to 7? You can already do a little bit of a sneak and try to get it right away. How could you get to square 7 if you know that after round 2, these are the probabilities? Well, you could have been at 1, 2, 5, or 6, and there's exactly one roll that gets you there. Or you could have been at 2 and 3 and rolled to get to the 4 and get to the 7. So, like, if you are trying to like speed run the original problem, it's 6 plus 2 plus 3 plus 4 plus, that's it, plus 6 plus 2. So that should add up to 23. Does it add up to 23? Yeah, it does. Okay, great. So 6 plus 2 plus 3 plus 4 is all these ways. So you could have been at 2, 3, 4, 5, or 6 and rolled to get to 7, or you could have been at 2 and 3 and rolled to get to 4. And so this is the original answer to the question that I asked, and that's the sort of super fast way to do it. You do this thing to get to this probability vector, and then you just say, how do you get to 7 from here? But let's do the full proper question, which is to find all the probabilities. So I'm going to answer the question over here, which is really tell me all the values of x. Okay, and so far we've done this and this, the first 2 rungs of the ladder. We're going to do the 3rd rung of the ladder right now. Okay, let's do it. Okay, so again, all you got to do is copy the numbers into how you move. And there's 6 ways to get to square 2, and so how could you get to the 6 ways to get to square 2? Those will translate into more ways to go. And I think it's going to be 6, 6, 6, 6, 6, 6, right? If there's the 6 ways to get to square 2, and then you can roll a 1, or you can roll a 2, or a 3, or a 4, or a 5, or a 6. That's the number of ways starting at square 2 to get to all these things. You can never be on square 1, so this one's all blank, all zeros. What about square 3? I guess this one will be 2, 2, 2, 2, 2, 2. And then square 4 is blank again. Square 5, you get 3, 3, 3, and then I believe it should be 9. Right? So there's 5 ways to be at square 3, and then you can roll a 1 or 2 or 3 to get to 6, 7, and 8. And to get to square 9, you can roll anything higher than a 3. So you can roll a 4 or a 5 or a 6. There's 3 rolls that will get you there, and there were 3 ways to get to square 5. So 3 times 3 is 9 ways to get to square 5. 9 ways to get to square 9 from square 5. Question over here, yeah.
Would it be good to use just copy the previous rows from 2 to 7, because that's what we already have.
Yes.
So if they're going to be identical, just multiply by number and then just
Yes.
do 9.
This is absolutely true. Yeah. So I think what you're pointing out is the operation that I'm doing in the green and the operation I'm doing in the yellow are essentially the same operation, and we're going to find a way to shorten all this. So don't worry, the whole course won't be doing this. This is just to show you for the first class. Yeah, great. Okay. That's S5. Okay, S6. I guess it's 4, 4, and then 4 times 4 is 16. Right. So there's 4 ways to be at square 6, and then you roll a 1 or a 2 or a 3 or higher. Okay, and then it's 8, and then I guess this one's like 40. Yeah, 5 rolls to get you there. And last but not least, if you're on square 8, that's 0. If you're on square 9, then there were 13 ways to be at square 9, and you're still at square 9. It's tempting to put 13, but you got to put 13 times 6, because you can sort of roll anything on the dice. Okay, 6 times 13 is 78. Okay. So there's my my thing for round 2, sort of repeating the operations. Now the probability multiplier is 1 over 216. 1 over 216 for all of these. Okay. I'll just write a few of them to give you the idea. Okay. Questions or comments before I add them up? Let's add them up. Now you gotta add them up. So before we apply the snakes and ladders, how could you have gotten to square 3? There's 6 ways. How could you have gotten to square 4? There's 6 plus 2 is 8 ways. Then 8, and then 11, and then 15, and then 23. Hey, that's the number that we were looking for. Is that the number we were looking for?
No,
That's a different one. Okay, so just a coincidence. And whatever is left over goes here. Okay, I'm gonna do a little sneak again and just copy it over from here. Should be 145, 145. 6, 8, 8, 11, 15, 23, 145. Okay, 145. And now we apply the snakes and the ladders. So if you were in square 8, there were 23 ways to get there before the snakes and ladders. This moves you down to square 2. So you get 29 ways to be in square 2. Nope, that's square 3. 23 ways to be in square 2. Did I get that right? Okay, yeah, good. And then if you were in square 4, that moves up to square 7. So there's 23 ways. 15 plus 8. And there you go. 8, 11, and 145. So these are the probabilities at the end. Well, the numbers. Did I make a mistake? Okay. All right. So is this method easier or harder than the sort of brute force way? I claim that it's easier. So 1 is that it's sort of the same amount of work every time. And 2 is it requires very little creativity. So if you sort of know the rules to move from square to square, then it's quite easy to implement it. Of course, it's still kind of annoying, but we're going to see fast ways to do it on a computer. And this really is the like Markov process or Markov chain way of thinking is always try to think of updating the probabilities in some nice way because you have this Markov property that it doesn't matter how you got somewhere. The only thing that matters is where you are. So this kind of, we're kind of going up one rung of the ladder at a time. If you try to go up like and just do it from scratch, this is very complicated, hard. And this one is like easy 3 times. Easy 3 times. So that's the idea. And we're going to see smarter and smarter ways to do it, but it's a big idea in the course. Okay, let me put this one up one more time. Questions or comments about the solution? Okay, now we're going to try to accelerate this. This is the only course where we get only lecture in the course where we get nitty gritty and actually write out numbers. We're going to see smarter and smarter ways to do it. And the question for you is, did you recognize what kind of operation is sort of happening over here? This thing that I just did has a name in a course that you've taken already. And I want to see if you recognized what is the name of that thing. And I made a question in Mathematize called adjective. And it says, consider the function that maps the vector of probabilities after t rolls into the vector of probabilities after t plus 1 rolls. So that's exactly something that takes as input this thing in line 5. So it took 1, 1, 1, 0, 1, 1, 1. And then it mapped it into this thing, 6, 2, 0, 3, 4, 8, 0, 13. So this is a vector. That was a vector. It turned this vector. We did some stuff to it. We got this other vector. And then we took this vector and we did some stuff to it. And we got this vector, right? So it's a function that inputs a vector and outputs a vector. And it tells you what happens at time t. You feed it in, you do all these operations, and you get at time t plus 1. So that's some function. And the question is, what is a possible adjective to describe this function? So this function should ring a bell to you, or this type of function. And I want you to put in your answer. And it's a free form, put in any words you want, and we'll get a cool word cloud. So I'll give you guys a couple minutes to think about that. Okay. Let's say a minute. Because, yeah, it's just if you've seen it before or not, feel free to put in I don't know if you really have no idea, but it's more fun to take a creative guess. All right. Okay, time is up. Put in your favorite adjective. I guess you can put in I don't know if you really have no idea, but it's fun to see your guesses. Yeah, if you really don't know, put in I don't know. But yeah, okay. I guess I'm waiting for one person maybe who's not going to get the mark in time. Okay, I'm doing it. I'm pressing a button. Okay, here we go. Reveal counts. Okay, word cloud. I don't know. Very common answer. Okay, great. So what else we got? Iterative. I will say the whole thing we're doing is iterative, right? Like we start with one thing, then we do something, then we do something again. So the whole operation is iterative, but I'm asking you about each step, right? So what is each step? The whole operation is iterating this function over and over again. Like we applied the same function twice. What can you tell me about the function? What else did people write? Let's see. Next biggest I think is linear. I like matrix E. That's cool. Let's check out. Now we can read the individual lines. I don't know, 4 people, great. Iterative, 2 people. I don't know, also very good to know. Linear regression. I would say it's not linear regression, but it is linear. It is a linear function. Cool, yeah, that's also absolutely true. Okay, it is not a well, I don't know if it's a contraction mapping or not. I don't know. Matrix E, this is the best answer. I like that the best. Okay, matrix E, it is matrix E. What do you mean by it's matrix E? So I think the most correct answers are linear and matrix E. So let's write this down. So the operation to go from one probability to the next is probability vector. And by a probability vector, I mean like the probability that you are at location x. Let's write it as a vector. Let's call it p sub t, and it's a vector. And it's why is it a vector? Because you can be at location 0 or at location 1, and that makes a vector. A location 1 ... all the way up to at location 9. I guess they're squares. Maybe I could have called them squares. Okay, so it's a vector of length 10. At time t. At time t. And we're talking about how do you go, let's call it f. F of pt equals pt plus 1. Pt plus 1. And what can we say about this function f? And there's 2 things about f that are absolutely true. F is, it is linear. Linear. What does linear mean? Linear means that if you do a linear combination of like entries of pt, you'll get like a linear combination out in pt plus 1. Or another way to say it is that the entries of pt plus 1 are a linear combination of the entries of pt. Why was it linear? Well, look at the operations we were doing. So the operations we were doing were in the spreadsheet here. And what were the operations, right? It was like here's an example, right? We took this 6. Whatever this 6 was, we copied this number, we wrote it out a bunch of times, and then we added up what it was doing. If that 6 was replaced with a 7, then it would just like proportionally multiply all of these, and it would like add up in the final answer. So all these operations are linear. It's linear in the sort of entries over here. And I guess Gabe noticed that as well when we said this 66666 is 6 times bigger than 1111111, right? Like it's the same thing, but multiplied by whatever you input. So whatever you input just gets multiplied and gets scaled. That is a linear function. The other thing someone wrote, which is even more descriptive, is it's matrix E. Matrix E. Okay, and if you had a good linear algebra class, you should have been told that being linear and being matrix E are the same thing. All linear maps are actually matrix E. So every time you have a linear function, this is the reason linear algebra is so useful, all linear functions are actually matrices. Or I shouldn't say they're matrices, it's better to say they're matrix E. So you can write down f of the vector x equals something because it's matrix E. Does anyone know if you have a linear function and it's matrix E, what is f of x equal to? If you do something to the vector x. Yeah.
Vector?
What do you do?
Another vector?
It will be another vector. So f of x, right, is some other vector. What do you do to the vector x to figure it out? Yeah.
Multiply it with matrix.
You multiply by a matrix. So there is some matrix M, and if you do M times x, then you will get f of x. So every time there's a linear function, all linear functions are secretly matrix multiplication. This is like the moral of the story of linear algebra. All linear functions are matrix multiplication by some matrix. So anytime there's a linear function, that is actually matrix multiplication. This is why they'd make you do all these things with matrices. So if you had a good linear algebra course, this would have been the main message of the course. If you had a less good linear algebra course, they might have just tortured you and made you play with matrices all day and not told you what it was. So I don't know. Let's take a vote. Who had a great linear algebra course and remembers this lesson? Who got tortured? Okay, great. So good. We're telling you now. This is why they tortured you with matrices and made you do all sorts of things with matrices, is because whenever you have a function like this, there is some matrix over there. The good news is there's going to be a lot of matrices in this course, so maybe because you were tortured, you'll do good now. I don't know. Okay, so this is absolutely true. Normally, this is how you write matrix multiplication with the matrix on the left. For historical reasons, you write it the other way in this Markov chain stuff. I don't really know why. But the way we're going to do it, and the thing that is actually true, is two things. So one small notational thing is we're always going to think of these probability vectors PT, think of it as a row vector. This is important. So normally in linear algebra, you do a lot of stuff with column vectors. It's very important that the probabilities are always a row vector. You'll see that column vectors mean something else later. And we could have equally well lived in a universe where the probabilities are column vectors and the other thing is the row vector. But I don't know. This is what Mr. Markov came up with. So let's just say this is some convention that everyone uses. So it's important you don't mix it up. And because the PTs are row vectors, the matrix M actually multiplies on the other side. And so the update rule is like this. The update rule is, it is PT plus 1 equals PT, and then you multiply by the matrix M on the other side. So this is an n by n matrix. Let's draw the sizes, n by n. And PT is a 1 row by n columns vector, or column vector. And this is also 1 by n. So the sizes add up. 1 by n, the n by n gets summed over, and you get a 1 by n. All right. So that's the rule. So it turns out what we were doing in spreadsheet land, we were just multiplying matrices by hand. We were doing matrix multiplication the long way of writing out what happens to each row and column and then adding them up. This should remind you of matrix multiplication. And we were just doing matrix multiplication. So now the question is, now that we know it's matrix multiplication, what is the matrix? What is the matrix? And I want to go over here. Okay. What is the matrix M? M. And the matrix M, it has a name. It is called the probability transition matrix. Probability, or sometimes just the transition matrix. Transition matrix. And I'm going to use the notation from the textbook that we're sort of vaguely following. I guess they also call it P. Let me, okay, M stands for matrix, but M equals P, capital P. Yeah, okay, I'll go with P to match the textbook notation. S prime. So these are states. And so a matrix has row and column entries. The rows and the columns are indexed by the number of states. For the snakes and ladders example, there were 10 states. So S and S prime, they will be numbers between 0 and 9. And it's telling you the S row and the S prime column. So those are both states. And the rule is it's the probability to go from state S to state S prime in one step. So this is what the probability transition matrix is. It tells you how you're moving around in one step. And that, knowing what you do in one step, exactly lets you iterate and figure out the probabilities you're at any location. Let's do an example. Let's figure out what happens when s equals 0. What happens from state 0. So from state s equals 0. So this would be like p of 0 comma s prime. This is the 0th row of the matrix. The 0th row. Okay, and what is supposed to be written, it is the probability that you start at square 0 and then you end at all the various squares. So it's the probability you start at 0 and end at 0, and then it's the probability you start at 0 and end at 1, and dot, 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 all the way up to 9. Probability you start at 9 and end at 9. Start at 0 and end at 9, rather. Okay, so it's the probability starting at 0, so I put it in the 0th row. This top row tells you all these probabilities. And we actually calculated this. Let me move this over. The 0th row. So if you start at 0, can you end at 0? No. And there's a sort of a 1/6 chance to be at 2, a 1/6 chance to be at 3. So this is s equals 1, 2, and 3. So you can either roll a 1, 2, or 3 to be at squares 1, 2, or 3. There is no way to be at square 0. And there's also no way to be at square 4 because the ladder would have taken you up to square 7. So this is 1/6, 1/6, 1/6. So this is 5, 6, 7. Okay, and the rest are all 0. 0, 0, 0, 8, 9. Oh, I guess there's only 8, 9. Okay, great. So this is the top row of the matrix. And actually, we had this in our solution. You might notice this 1/6, 1/6, 1/6 thing. This is the top row of the matrix. It is exactly what we had in Excel. Here, it's this one, line 5. So right, 1, 1, 1, 1, space, 1, 1, 1, but they were all supposed to be multiplied by a 6th. That's exactly the first row of the matrix. And in fact, when we calculated this, this is the round 1 probabilities. What we were actually doing, is we figured out that p at time t equals 1 was p at time t equals 0 times the matrix big P. And p at time t equals 0 is the vector 1, 0, 0, 0, 0 times the matrix P. And when you do matrix multiplication with a vector that is a 1 and all zeros, that will pull out the first row of the matrix. So this is the 0th row of the matrix. How do I write this? 0, I guess, colon, 0th row of matrix. So when you matrix multiply, on the left, you are doing a linear combination of the rows. If you have a 1 in the 0th entry and all zeros, you just get a copy of the 0th row of the matrix. And that's what we did. Okay, so this all gels with what we've been doing so far. This 1 meant there was a 100% chance to be on square 0 when you started the game. And so what I'm trying to show you is that what we did in Excel in this first little line was matrix multiplication that only involved the first row. When we did the second part in green, it involved all the rows, and we can write down what the rest of the rows are. Okay, let's do that. I guess before I do that, it's going to be more of the same stuff, so there's a good chance to stop me if something is not clear. Maybe there's something about linear algebra you need a reminder of. Okay, so let's do more of the matrix. Okay, why don't I just show you the typed up matrix, since I did type it up. Here is what the matrix looks like. I guess another fun thing for people who are in CS. This method is sometimes called dynamic programming. So Markov is the name of the Russian guy. Dynamic programming, as far as I can tell, it just means Markov. Okay. Don't at me. Okay. Okay, matrix multiplication. This is the matrix P. There's the 0th row. And here's the full matrix. Okay. So what is the full matrix? Oh, I want to zoom out so I can see it, but then it gives me the headings. Okay, here it is. So here I've written it. It's a 6 because everything in the matrix sort of represents a number of ways, and the probabilities are 1/6 times the number of ways. So this is another nice thing about matrix multiplication. You can factor out constants. Every time there's a 0, I've drawn it as a dot. And I've drawn all the things. It should hopefully be correct. So the 0th row is the 1, 1, 1, 1, 1, space 1, 1, 1. The second, starting at square 1, there's 2 ways to get to square 7, because you can either roll a 6 and get there directly, or you can roll a 3, get to the ladder, and that takes you up to square 7. So that's why there's a 2. If you start at square 2, it's exactly the same as starting on square 1, which is very counterintuitive. But it's because if you start on square 2 and you roll a 6, you go to square 8, and then the ladder takes you back down to square 2. So it's like you've done nothing. If you roll a 6 starting on square 2, you're back in square 2, and that's kind of why they're the same. You'll also notice here in the bottom, if you start in the 8th or 9th row, that means starting in square 8 or square 9, then there's 6 ways you can go to square 9. The probability is 1/6 times the number of ways, so you have a 100% chance of being in square 9. So starting in square 8 or 9, you just stay in square 9 after that forevermore. Okay, there was a question? Maybe not? All right. Any other questions or comments? Okay, so one more definition for you. So what definitions have we learned? Some of them are up here. Okay, here are some key questions we're supposed to be doing. What is a Markov chain? A Markov chain is the name for this kind of thing that we have just done. The snakes and ladders is the perfect example. Let's write down these definitions. So just to wrap everything up. So when someone says Markov chain, it just means a sequence of random variables that obeys the Markov property. Okay, and the good example to keep in your mind is if you make a sequence S0, S1, S2, ... where S sub t is the random variable that tells you at time t where are you. So this is which square you're on at time t. That sequence of random variables is a Markov chain. Which square you are on at time t. So it's a random variable because you could be on a number of squares. And the thing we've been doing so far is figuring out stuff about this probability vector, pt, which is the vector, the probability that st equals 0, probability st equals 1, ... all the way up to the probability st equals 9. So the Markov chain is the random variable. These probability vectors are the probability that it's in certain places. The Markov property says that st plus 1 depends only on st and not st minus 1, st minus 2, etc. So if you know where you are at time t, that's the only thing that determines where you will be at time t plus 1. How you got to the state does not matter. It just matters where you are. This is the sort of math version of the Markov property, and there's even a more mathy version that's on the website, but maybe not. I won't say it out loud. Markov property in random variables. The transition matrix we did, that's the other big definition that you're going to need to know. The transition matrix. And this is the matrix of the operation that takes pt to pt plus 1. So pt plus 1 equals pt as a row vector times this big capital P. And that capital P has the interpretation of the probability of going from one state to the other state. S prime, let's write it down one more time. Probability st plus 1 equals s prime given st equals s. That's the math notation version of what we said in words before. There's one more definition that I haven't said yet, which is something called a terminal state. A terminal state. I have not yet used these words, but you might be able to guess what it is. Does anyone want to take a guess of what do you think it means when someone says a state is a terminal state? Yeah.
Like square 9,
Square 9 is a terminal state. So what about it is terminal?
like you're done when you get there.
Yeah, you're done when you get there in the sense that the game is very boring. Once you're in square 9, you just stay in square 9 forever. So our terminal state is a state S such that P of SS equals, I'm going to say 100%. 100% is also known as the number 1. So if you're in state S, you just stay in state S forever. You can see that in the matrix that we wrote before. And it's sort of like you stay there forever. And because you stay in a terminal state forever, you can sort of like stop your game and just say like, okay, we know it's over. Nothing interesting is going to happen once you're in the terminal state. And we saw that on our matrix over here because, let's see, the entry of the matrix in the 9, 9 entry of the matrix is 1. Note that square 8 is not a terminal state, right? Square 8 always leads to square 9, but you still have one step to go. So if you're on square 8, you're not done the game yet. But on square 9, you are done the game. Okay, yeah.
So if you Alex, when it comes to the issues of state 4 and state 8, what do you mean, given that you can never really start?
Yes.
there until you-
Yeah, this is a good point. So in the way I did this, you'll notice that the column of 4 and the column of 8 are all zeros, which is saying in this Markov chain that I have written over here, there is a 0% chance to end up in square 4 and a 0% chance to end up in square 8. And that's totally fine. Like there's some states that you will never reach. That's a valid thing that can happen in Markov chains. I will tell you, if you guys want, I'll post this online. If you watch the rest of the video, so we watched the first 3 minutes. In the last 18 minutes, they make the matrix and they use it to solve something and they leave out 4 and 8. So they're like, just don't even put it in your thing. You could equally well make a Markov chain and exclude 4 and 8 from your system and say, I'm not even going to count those as states. And it's up to you how you want to do it. We're going to do the stuff they do in the video later in the course, probably next week. So you can check it out if you want spoilers, I guess. Okay, any other questions or comments? There's 1 minute left. Okay, so do check out the course website that has all the stuff we did from today and a little bit of the stuff we'll do next class. That's the kind of thing you're going to do for the exposition. You'll write up some notes. Here's like a copy of the stuff I did, right? And like some text with like what I said. That's the kind of thing that you'll be doing for the exposition assignment. Okay, I'll be around for questions. See you guys on Tuesday.